Hello everyone, my name is Yuanhao Lyu, and I'm the first author of this paper, and I'm from Vanderbilt University, USA. Today I'm going to present our work, The Effect of Crowds on Peripersonal Space and Interpersonal Distance in Immersive Virtual Environment. As VR becomes more social and immersive, understanding how crowds affect personal space is crucial. In virtual gathering, users must adapt their comfort zones to dense and dynamic crowd. In contrast, VR game, for example, The Last Hope, push this boundary even further, where the threat such as monster raises the question, how close is too close? How do virtual entities shape our sense of safety and personal boundary? This brings us to self-avatar, where personal space around self-avatar plays a key role in how we interact with others in a virtual environment. But how does that change when we're surrounded by a virtual crowd? In this study, we investigated the relationship between crowd density and embodied personal space in VR. Understanding this is not only important for theory, but also has practical implications, from designing more comfortable social VR experiences or creating therapeutic applications that adapt to users' comfort level in crowd. In short, we aim to understand the question, how do you feel when the crowd surrounds you in VR? In this work, we break down personal space in two terms. First, interpersonal distance, or in short, IPD. This refers to the physical distance that individuals naturally maintain with others during social interaction. This idea is first brought up by Hall in 1966, where IPD is contextual and it shrinks and expands based on social comfort with others. Next, peripersonal space, or PPS. PPS can be thought of as the extension of the body. This is the space immediately surrounding our body, often associated with safety and interaction. As you can see in this figure, PPS represented our personal safety bubble. When something enters our space, it can trigger a fight or flight responses. PPS is registered by the head and limbs. PPS is also contextual. It can expand and shrink depending on the perceived threat or safety level. So what's the difference between IPD and PPS? In sum, IPD refers to social comfort zone with others, and PPS refers to our action space and our personal safety bubble. Now that we introduced the concept of interpersonal distance and peripersonal space, the next step is to ask the question, how do virtual crowds actually influence them? And how do people who feel comfortable in crowds versus people who feel stressed in crowds respond to them differently? To test these questions, we formulated four hypotheses. H1 and H2 stating that increasing crowd density will lead to a smaller IPD and PPS. H3 and H4 stated that individuals with a positive reaction to the crowd will exhibit shorter IPD and PPS compared to those who do not. And please refer to our full paper for the detailed background and reasoning behind our research question and hypothesis. Our study is a within-subject design where participants were introduced to three crowd scenarios with a Unity-based environment. We have utilized Microsoft Rocketbox Avatar Library to design all of our environment. For participant recruitment, we have recruited 54 participants, which their age ranged from 18 years old to 45 years old, with a balanced distribution of genders. We built a 30 meters by 11 meters virtual room for our three crowd conditions: a no crowd condition, a medium crowd condition with a crowd density value of 0.3 avatars per square meter, and a high crowd condition with 0.8 avatars per square meter. These numbers were carefully chosen based on crowd literature and our design choice. The details are explained in our paper. To make our environment feel more realistic, we also accompany the scene with spatial chatter noise to enhance the realism of our VR environment. We also purposely placed the avatar directly in front of the participant view so that they were noticeable during our VR task. Before beginning the VR task, we calibrated each participant's self-avatar. To support embodiment, we provided a set of pre-defined avatars representing different races and matched them as closely as possible to participants' self-reported race. We also adjust height to ensure the avatar align with participant real body height in VR. Below is an example of an Asian female and male participant calibrate themselves in the self-avatar in VR. Next, we give participants 40 seconds to observe our VR environment in three crowd conditions to get accustomed to our scenes. In each crowd condition, we will measure IPD and reaction time for PPS extraction. For IPD, we use a similar approach by Zilberg et al., where participants are instructed to press the trigger when they felt like the avatar was at the closest distance which they felt like comfortable interacting with. Thus, their IPD is recorded by the trigger press. For PPS, we chose a diagram used by Sereno. While maintaining eye contact with the approaching avatar, there will be a pulse delivered sent to participant handheld controller. The pulse will randomly be delivered at 1 meters, 1.25 meters, 1.45, 1.85, and 2.15 meters in front of the participant. Participants were asked to press the trigger immediately after they felt the vibration to record their reaction time. We have selected 8 avatars for our PPS task and 10 avatars for our IPD task, which covers a wide range of cultural background and profession. All trials for our task and conditions are counterbalanced to avoid bias. Besides our VR task, we also collected surveys and interview data to better understand individual differences. We asked participants to rate their comfort level with different crowd density using the Likert scale. If they reported a strong reaction, we follow up to determine whether it reflects stress or relaxation. We also include open-ended questions to capture more details about the experience with crowd density. To measure how participants perceive their peripersonal space, we fitted the reaction time data as well as the pulse delivered distance data to this ski model curve. This curve shows us how quickly people respond as an avatar approach. The shape of the curve let us identify 2 key parameters. First, the XZ value, which is the PPS boundary. This marks the distance where the reaction time shifts most sharply. Second, the inverted slope, or B value, tells us how clearly and confident participants could define their peripersonal boundary. A steep slope, meaning a smaller B, shows they were confident about their PPS boundary. A shallow slope, meaning a larger B value, shows more uncertainty, meaning the boundary felt blurry and harder to pin down. Let's jump into our results section. First, this table shows our crowd reaction group, where we have 17 people in the indifferent group, where participants felt little to no difference with the increasing crowd density. Next, we also have 17 people in the crowd comfort group, where people felt comforting with the increasing crowd density. We also have 20 people in this crowd stress group, where people felt stressed with increasing crowd density. For our data, we use a mixed factor ANOVA to analyze the effect of crowd density on IPD, PPS boundary, and PPS slope across all 3 crowd reaction groups. For our IPD result, interestingly for IPD, we did not find a significant interaction effect between crowd reaction group and crowd density conditions. We found that IPD significantly decreased when the crowd density increases. We also found a significant decrease between no crowd condition and a medium crowd condition. We also found another significant decrease between no crowd condition and a high crowd condition. Taken together, we can support our hypothesis 1 and reject our hypothesis 3. For our peripersonal result, we found that there's a significant interaction between crowd density and crowd reaction group. To break it down in detail, we found that in the crowd comfort group, PPS decreased significantly in no crowd condition between high crowd condition. For the crowd stress group, we found that PPS increased significantly between no crowd condition and the high crowd condition. PPS also increased significantly in the medium crowd condition and the high crowd condition. Now let's look at our slope or B value, which reflect how clearly participants define their PPS boundary. We found that there is a significant interaction effect between crowd density and crowd reaction group. For the indifferent group, which is represented by the green line, there is a significantly decrease between no crowd condition and the medium crowd condition. For the crowd stress group, which is represented by the purple line, there is a significantly increase between no crowd condition and the high crowd condition. So drawing from our result on PPS and boundary and slope, we can only provide partial support for our H2 and H4. PPS is dependent on the crowd perception. It contracted for the comfort group and expanded for the stress group. In the stress group, though, the slope showed greater uncertainty, meaning the boundary becomes less clearly defined as the density increases. This table highlights our significant findings. For IPD, across all crowd reaction groups, there is a significant decrease in IPD with crowd density. For PPS boundary, in crowd comfort group, there is a significant decrease with crowd density. Also, in the crowd stress group, there's a significant increase in PBS value with increasing crowd density values. For PBS slope or B value, in the indifferent group, there's a significant decrease with crowd density values. And in the crowd stress group for our B slope, there's a significant increase with crowd density values. In conclusion, our result matched prior VR result, showing people maintain bigger IPD in virtual settings. For our no crowd setting, our IPD averaged about 1.89 meters, which is much larger than Hall's original proximity ranges. When a crowd was present, IPD compressed, which reflecting social norm. Unlike PBS, IPD did not change with emotional reactions. So overall, we see IPD as a marker of social adaptation in VR. For PBS, we found that stress expanded PBS boundary while comfort contracted them, which is consistent with defensive buffering mechanism. Unlike IPD, PBS was highly sensitive to emotional reactions. Under stress, we also saw greater uncertainty in defining PBS boundary, suggesting a blurred PBS boundary. Taken together, these findings suggest that spatial behavior in VR is shaped by a dynamic combination of embodiment, emotional status, and social context. For future work, we plan to improve our crowd design by testing more density values and adding dynamic animation like upper body motion or gaze shift. We also want to recruit a large and more diverse sample size to strengthen our findings. Next, future work could also include direct measure of embodiment and uses more realistic self-avatars. Finally, future work will look at the roles of social identity, cultural background, personal trait to better understand why people perceive crowd differently in VR. Please see our full paper for more details. Thank you so much for listening.